These are the lesson 8.4 notes for day 2. Sound and decibels are what we're going to work with. And we want to show you how these are related to logarithms. So it's sort of an application on logarithms. We're going to start by converting decibels to watts per meter squared. We're going to use this formula here. It says L equals 10 times log of I over I sub O. L stands for loudness in decibels. I is the intensity of the sound in watts per meter squared. And I sub 0 is the lowest intensity sound that the human ear can detect. That value is 10 to the negative 12th power watts per meter squared. For example, to convert normal conversation, which is a watts per meter squared, to decibels, we're going to use our equation. L equals 10 times I is the intensity in watts per meter squared, so this is an intensity value right here. We're going to plug that in for I, over I sub 0, which is always going to be 10 to the negative 12th power. Now, one thing I've forgotten here is my log, so I need to make sure that that's in my equation as well. So L equals 10 log 10 to the negative 6th power over 10 to the negative 12th power. When you type this in your calculator, it should look sort of like this equation right here, or little expression. And we hit enter, and we get 60. So 60 decibels is what normal conversation sounds like. To find the intensity of a vacuum cleaner at 80 decibels, this is obviously louder. We're going to convert this to intensity by using the same formula, but this time we know the loudness. It's 80. This value is an L value, and we're going to try to figure out what I is equal to. So back to my equation again. This time I'm going to plug in 80 for L, 10 log. I don't know what I is. I'm trying to find the intensity. And I sub 0 is always 10 to the negative 12th power. So to solve this equation for I, here's what we're going to do. First of all, probably no surprise, we're going to divide both sides by 10 because, well, the 10 doesn't need to be on the right side. We're trying to pull everything off this right side of this equation. So I'm going to divide everything in this equation by 10. And on the left side, you know 80 divided by 10 is equal to 8. On the right side of the equation, I have log of I over 10 to the negative 12th power. Now, it would be nice to just multiply everything by 10 to the negative 12th power, but this thing we're taking the log of is basically grouped together. So you may remember, if you have a division problems can turn into subtraction problems when working with logarithms. It's one of our shortcuts. So we can say that 8 is equal to the log of I minus the log of 10 to the negative 12th power. And the log of 10 to the negative 12th power is something that you can crunch out. If you actually take the log of 10 to the negative 12th power, you end up with negative 12. And that should make sense because when you think about logs, we're trying to think of 10 to what power would equal 10 to the negative 12th power. Well, negative 12 would be your power. So we're going to replace the minus log of 10 to the negative 12th power in this problem. So what we have here is we have 8 equals log I minus a negative 12, which is plus 12. So next thing we can do is subtract 12 from both sides, and you get negative 4 equals log of I. To convert from exponential form to convert from logarithmic form to exponential form, what we're going to do is say this is 10, this is our base right here. 10 to the negative 4th power equals I, or you can say I equals 10 to the negative 4th power, and there's your solution. For our last question, how many more times intense is a vacuum cleaner than normal conversation? Think of the vacuum cleaner value here is 10 to the negative 4th power, and we're going to divide it by normal conversation, which is 10 to the negative 6th power. With exponents, you subtract the exponents, so this is going to be 10 to the negative 4 minus negative 6 power. Negative 4 minus negative 6 is equal to 2. So it's equal to 10 squared, and that's equal to 100. If you ever have to find out how many more times in 10 something is than something else, divide the two numbers and you'll get what that intensity value is. So that's equal to 100. A vacuum cleaner is 100 times more intense in sound than normal conversation is. Similar problem, a local concert hall wants to reduce the intensity of sound by 1/4. How many decibels less will the sound be? We're going to set a few variables here. We've got a present intensity and present loudness, and we're going to compare it versus a reduced intensity and reduced loudness. Now, first of all, I2, the reduced intensity, is going to depend on how much you want to reduce the sound by. And this fraction will change depending on the problem. If we're trying to reduce the intensity by 1/4, that's like 25%. And if we take away 25% from 100, this kind of gets you your scale factor of 0.75. So I want the intensity, the reduced intensity, to be 75% of the present intensity. We're reducing it by 1/4, which is the same thing as 25%. And if you reduce it by 25%, it's like subtracting it from 100%. So the intensity will be 75% of what it once was because we're reducing it by 25%. Now we have our loudness formula from the top of this page. Loudness is equal to 10 times log I over I sub 0. Now in our problem, it's going to be 10 times log of I sub 1 over, it's always I sub 0. And for the reduced loudness, it'll be 10 times log I sub 2 over I sub 0. So it's always over I sub 0. I'm just saying the present loudness is equal to 10 times the log of the present intensity over I sub 0. And the log of the reduced loudness is equal to 10 times the log of I sub 2, the reduced intensity, over I sub 0. How many decibels less will the sound be? Well, to calculate how many decibels less it will be, we'll subtract the two intensities, which means we're going to replace L1 and L2 with these formulas that we just calculated. 10 times log I sub 1 over I sub 0 minus 10 times log I sub 2 over I sub 0. Now we're going to work on simplifying this expression. First of all, we've already calculated I sub 2 is equal to 0.75 times I sub 1. So I'm going to replace I sub 2 in this problem with this value. We're just going to do some straight up substitution. 10 times log I sub 1 over I sub 0 doesn't change, minus 10 times log I sub 2 is 0.75 I sub 1 over I sub 0. All we've done is substituted for this value right here. We continue to work this problem out here. On the right side of the equation is where things are going to change. I'm just going to rewrite kind of our left side here. Just bring this straight down. Minus 10 times log. And I'm going to bring the 0.75 down. This is going to be 0.75 times I sub 1 over I sub 0. Really not a huge difference here. We're just kind of bringing this out front. We still have the fraction I sub 1 over I sub 0 here. For our next step, not going to mess with the left part. 10 log I sub 1 over I sub 0 minus 10 times log. Because this is a multiplication problem, you may remember we can turn multiplication problems into addition problems when working with logs. So what I'm going to do is I'm going to say 10 times, I'm actually put parentheses here, and I'm going to do the log of the sum, or the sum of the logs, excuse me, log of 0.75 plus log of I sub 1 over I sub 0. So what's this equal to? Well, we're going to have 10 times log of I sub 1 over I sub 0 minus, distribute the 10 times log 0.75 minus, because we have a negative times a positive, 10 times log I sub 1 over I sub 0. What did we do? We distributed the 10 to both of these terms inside the parentheses. Now, if you're wondering why we didn't substitute the first term here, it's because 10 log I1 over I sub 0 is the opposite of negative 10 log I sub 1 over I sub 0. These will cancel. And the good news is that this expression right here is something you can find on your calculator. Let's do that. Negative 10 times log 0.75 equals 1.25 approximately. And that is how much different, or how many decibels less, the sound will be. It is a loudness value, so it is appropriate to list this answer in decibels as well. And that's how you reduce noise, and that takes care of sound in decibels and how it's related to logarithms.